In this video, I'm going to show you where the graph of trigonometric functions comes from, or the graphs rather. We'll look at sine, cos and tan. We'll look at the various features and how we can do transformations on them similar to any other function. So to start with, just explaining what the graph of a trig function actually is. What we're doing is graphing x, or the angle in the unit circle, against sine x, which of course is your y value. That's a terrible unit circle. That's okay. So we're actually calling this x, this little angle in here, and what we're graphing is sine x, which is the y value. So as this goes around, graphing what is the vertical distance there as we go around. So that's for the graph of sine x. Obviously, cos x would be graphing the horizontal. Just a tip, do get used to using radians, okay? As we get into more advanced trigonometry, we tend to use radians more than degrees. You need to be able to switch between both, but you definitely need to be getting comfortable with radians. A little bit of terminology, just to kick us off, and then I'll show you what the graph actually looks like. A cycle is one complete round trip of the function. So you'll see when I show you the graph that it's a repetitive function. It just keeps going indefinitely in either direction, but it repeats. So it's got a specific cycle, and each time it starts repeating its new cycle. The period is how long until the function repeats, and that's in terms of x. So when we graph the function, that's the distance along the x-axis. So we talk about that either in degrees or radians, depending on what we're working in. So that's in degrees or radians. And the amplitude is basically the height of the function. It's the distance between the mean y value and the maximum or minimum y value, or you can think of it as halfway between the maximum and the minimum. Now, probably this doesn't make a lot of sense until you've actually seen a function. So let's jump over to GeoGebra and have a look at a function. So we're going to look at sine, the graph of sine x. Okay, so x is the value of the, or in this case it's theta, but that doesn't matter, the value of the angle as we go around here. So you can see that when theta is 0, we know that sine of theta is 0 because there's no y component, there's no vertical component. Now as we drag this along, oops, there we go, you can see as this gets bigger, the height is getting bigger, so this is tracking up here. Okay, and we keep dragging that around. Oops. And you can see it's making that until we get right up to there, up to sine of 90, which we know is 1, so that's the peak of the function. Now as we go around a little bit further, we go around to 150, it's coming down, and you can see what's going to happen hopefully at 180. You'll find it gets back to 0. Okay, so it's gone up and down. Of course, once we get down this side now, we're going to the negative y territory. So it's negative, the function becomes negative, and all the way around back to 360. So you can see it makes that wave, which of course is where the term sine wave comes from if you're thinking about sound or sort of radio waves and transmissions. Okay, so that's the graph of sine. So let's go back over here. Okay, so here's our sine function. So in terms of the terminology that we're talking about, this is a cycle here where you start at 0 and we go up and down and we come back, and at this point it's going to start repeating itself. So that's a cycle. Okay, a cycle could also be from here, when we go from 1 and back up to 1, or from -1 and back down to -1, it doesn't matter. Any point from which the function starts repeating itself. Now, so that's one cycle, and the length of that is the period. So the length of the cycle is the period. Now, for the basic function of sine x, in this case it's 2 pi, or 360 degrees, which makes sense because when you're in a unit circle, it's 360 degrees for a full revolution. Okay, the amplitude is this distance here. So the distance from the mean, so the mean value, which in this case is at 0, up to the maximum y value, okay, which is 1 here, max y. So amplitude equals 1. Alright, but as you'll see a little bit further down the track, we can actually translate this whole thing up and down. So we could shift the mean up to 1, and then your maximum point would be at 2. So it might be helpful to think of it as the amplitude is halfway between the max and mean. So we can also do that. Halfway between, BW means between, max and min, sorry, I think I said mean. Max and min. Okay. One other thing that we talk about sometimes is odd functions, or whether functions are odd or even. And to determine this, you need to look at what happens when you reflect them. Okay, so if we do a reflection of minus x, that means reflecting in the y-axis, so reflecting horizontally, going this way to this way. Okay, if we reflect that way, we'll see it has the same effect as if we were reflecting in the x-axis, about the x-axis. So if we reflect about the y-axis, you can see this would go over here, we'd end up with a peak here and a trough here. And if we reflect in the x-axis, it does the same thing. We have a trough here and a peak here. Okay, so that makes it an odd function. So when f of negative x is equal to negative f of x, that's an odd function. Alright, so the next one's the cosine function. Let's jump back over to GeoGebra and have a look at that one as well. Okay, so we've got cosine. So much the same. Of course, now we're measuring the x distance. So this one's sort of a little bit trickier to see, I guess, because what you're actually measuring on the y-axis is the x distance. So sort of a little bit hard to see there, but it's the same deal. So we can see we start at 1 because we know that cos of 0 is 1. And as we come across here, it comes down through 90 degrees, down to a minus 1 at 180, back up through, and up to there. So it actually looks exactly the same as the sine function, except instead of starting at 0, it starts at 1. Okay, but the period is the same, the amplitude is the same, the shape is the same. So it's had what we call a phase shift, where the whole thing's been shifted over. So if we go back over here and have a look at that, and this should say cos, not sine, sorry. So we have the same thing. Okay, period is still 2 pi. The amplitude is still 1. Oops, amplitude equals 1. Okay. But this is what we call an even function. So what that means is if you reflect it around the y-axis, so cos of minus x, you reflect it around there, it actually doesn't make any difference at all, because this is a line of symmetry down here. So we say that cos of minus x is the same as cos x. So we've got f of minus x is the same as f of x. And that's called an even function. So if you're doing exercises out of Sadler's book, he talks quite a bit about odd and even functions. So when we compare the two graphs of cos x and sine x, as we saw, they've got the same shape, same amplitude, same period, well, all that sort of thing, but they're a little bit offset, so we call that a phase shift. So here we've got the graph of sine x in red, and we've got the graph of cos x in green. Okay, and what we say is the graph of cos x is the graph of sine x translated pi on 2 units left. Okay, so if you imagine you took sine x in this point here, move it pi on 2 units, okay, or 90 degrees left, and that maps it onto cos of x. Alright, so using our transformations, we can say that sine of x plus, remembering this means move to the left, x plus pi on 2 actually equals cos x. And you'll find that does come in handy a little bit further down the track when we start doing trigonometric identities and proofs and things like that. Okay, so that's a phase shift of 90 degrees or pi on 2 units. Right, now tan is a totally different matter. Okay, tan doesn't look anything like sine and cos, and the reason for this is because when we go and have a look at our unit circle for tan, okay, remember when we were finding what the tan value is, we actually extend out beyond the unit circle. So we go find the angle, pick that point, but then we project that out to where it meets this vertical line that's a tangent to the unit circle, and we're measuring that height there. And then as we come around here, then we project down. So at theta equals 0, it's obviously 0, but then it gets larger quite quickly, so up to 45 degrees it's at 1, and then it just keeps getting steeper and steeper and steeper. And of course at this point, as we approach 90, it's approaching vertical, and this line's vertical, so when you get to 90, it's undefined, because they're parallel lines, so there is no intersection. This line does not intersect with the parallel line. So that's when you calculate, if you put tan of 90, it'll go, no, can't do that, math error. Okay, so it's undefined. So of course on a graph, when you have an undefined point, that means an asymptote. Alright, and then when we come over here, we're projecting down, now we're in negative value, so it's coming up from minus infinity, it's coming up back here, up through 0, at 180. Okay, so at 0 there. and then going off again. It goes off. Whoa, another asymptote there. Okay, and then back up to 0. Alright, so that's why you get these funny looking sort of curves and then asymptotes in between, because you've got undefined values at 90 and at 270. So it's a little bit different in terms of period as well. Okay, so you can see that the repeating point, if you start here, a cycle would be up and then back to here. So the period of tan x is pi, not 2 pi. So it's actually half. So it's pi or 180. Okay, amplitude doesn't have any meaning because these extend infinitely. To plus infinity, this extends down to minus infinity. So amplitude doesn't make any sense, doesn't have any relevance. Okay, but you do have to think about the asymptotes. And so you've got these repeating asymptotes, and you need to be able to find or define where they are. So what regularity they are and where they occur. Okay, in terms of domain and range, so for sine and cosine, the domain is all the real numbers. They extend infinitely in either direction. And the range is obviously the minimum value to the maximum value. Now that depends on whether you're doing y equals sine x, or if you've done a horizontal or vertical dilation on it, rather a vertical dilation, or a translation. Okay, so you just need to find the minimum and maximum values. For tangent functions, the domain is all the real numbers except for the repeating asymptotes. So there's just those regular values of x that tan is not defined for. The range, on the other hand, is all the real numbers because it goes from minus infinity all the way up to plus infinity. So it's all the real numbers. Okay, so looking at transformations. Transformations work on trig functions exactly the same as they do on any other function. So we've got a, this one's your vertical dilation, okay, of dilation of scale factor A. Over here, you've got your horizontal dilation, and of course that's of scale factor 1 on B. Remembering when it's the x, it's sort of the reverse of what you think. This is your horizontal translation. And this is your vertical translation. So remembering that you need to be careful about order. In this case, you have done a horizontal translation first and then your horizontal dilation. Okay, so you replaced it with x minus c and then just replace that. So this is horizontal translation, then dilation. So make sure you get it the right way around. Okay, otherwise you'll end up with something that's not quite right. I'm just going to pause the video here and we'll do some examples in the next one.